Now, question one, you are given two isotopes of nickel, okay, and then you are supposed to read all the statements and see which one is true about them. So A, the electron arrangement of both these nickel 2 ion is 1s2, 2s2, 2s, 3s2, 3p6, 3d6, and 4s2. Okay. Now what happened is, although they are isotopes, they have the same number of proton. Okay, that means they will have the same number of electrons also. Yeah, so only the number of neutrons will be different, and therefore the nucleon number will be different. So if they have the same number of protons and electrons, they should have the same, okay, arrangement for the electrons. So nickel is 28 proton number, okay, or the number of electrons for nickel as a neutral atom is also 28. Okay, so let's write the electronic configuration for nickel using the proton number. Yeah, I'm writing for atom, not ion yet. Yeah, only the atom. So 1s2, 2s2, 2p6. Usually until shell number 2, you use 10 electrons already, so 18 to go. 3s2, 3p6. Now, most of you recognize that 4s orbital has lower energy than 3d orbital. So you fill in 4s orbital first. So up to here, 20 electrons. Okay, so 8 more will all go to 3d orbital. Yeah. Okay, that's how I always write the electronic configuration for transition elements. I know shell number 1 until number 2, okay, 10. Then 3s, 3p, 4s, another 10. Then the remaining, okay, I write in 3d orbital. Why? Because 3d orbitals can accommodate maximum 10 electrons. Okay, so 8 all will go to 3d8. Okay, now nickel 2 plus here, that means must lose 2 electrons. Okay, lose 2 electrons. This is the tricky part about transition elements. When you fill in the electrons, you fill in 4s orbital first. Okay, but when you remove electrons, okay, you also remove from 4s. You'll be wondering, hey, how come? Okay, teacher just said that 4s orbital has lower energy than 3d. That's why I fill in 4s orbital first. How come suddenly when I remove, right? I don't remove from 3d. 3d should be outside, right? No, after 4s2 and 3d8, they have electrons. Okay, repulsion between the electrons will push 4s shell number 4, okay, to go out further away from nucleus. That is why after they have electrons, okay, 4s will actually go out, okay, further away from nucleus. So when we remove the valence electrons, right? So now 4s becomes the valence electrons, the outer shell. So 2 positive here, we need to remove 2 electrons from 4s orbital. So nickel 2 plus, okay, I have to remove these electrons, so it becomes 4s0. So now let's check, yeah. So the electron arrangement for both these nickel 2 ions is 1s2, 2s2, 3s2, 3p6, 3d6, 4s2. This part is not correct. Okay, it should be 3d8, 4s0. So A is not correct. Now B. The nickel 60 2 plus will have more protons in its nucleus than the nickel 58 2 plus ion. Okay, now this is another isotope, okay, of nickel 58. The difference is only the number of neutrons. So that is the other part of the definition, different number of neutron. So not proton, yeah? Not different in number of protons. So this part is wrong. B is not correct. Now C, in the same strength magnetic field, the 60 nickel, it will be deflected more than the nickel 58. Okay, this one deflected more. Now which one will be deflected more? Okay, is the one that is lighter. Yeah. So if you have two, you look at the angle, this one bigger. Okay, deflected more, bigger angle, okay, deflected more. Okay, deflected more one, that means very light or lighter, easier to, okay, be deflected. So this is lighter. Then this one smaller angle, deflected less, okay, heavier. So you look at the number, this 60 and 58 actually representing another thing of another property of nickel, which is the mass, okay, of these two isotopes. So 60 higher number, 58 lower. So this is heavier. Okay, this one lighter. So the heavier will be deflected less, but here there are more. Okay. So again, this is not correct. This part is not correct. So C is again wrong. So our answer should be D, but let's still go through and check. Yeah, both nickel 2 plus ions have the same number of electrons, but different number of neutrons. Yeah, okay. Let's look at the definition again. Same number of protons means same number of electrons, but different number of neutrons. So correct, same number of electrons, but different number of neutrons. So the answer to question 1 is D. Okay. Now, question 2, you have this diagram showing you how, okay, a sample of this americium element was vaporized, ionized, passed through electric field. Okay. Then they give you the angle. So analysis of the deflection occurring at the electric field region reviewed the following data for sample of americium, okay, 241. Now, it was observed that a beam of the cation gives an angle of deflection of 2 degrees. Okay, this bond angle is 2 degrees, this cation. Now, why cation move to the negative side? Because positive and negative charges, okay, attract each other. And then now, what would be the angle of deflection of a sample of singly charged calcium ion? So we are supposed to compare these two now, yeah? Okay, first we have, okay, americium 241 plus, okay? Now they want you to look at calcium also plus, okay, but they didn't give you, okay, they didn't give you the proton number or the nuclear number of calcium. So let us just look at this periodic table. Okay, calcium here 20 proton number. Now americium also I need to find, okay, which is here 95. Okay, let's go back. Yeah, so this is 20, this is 95. Okay, and for calcium, okay, go back to periodic table again. Calcium 40.1 is the mass number. So that means the total here will be 40.1 also. Of course, it's an average of all isotopes, yeah, but roughly very close. So this americium, okay, 241, okay, calcium 40. This one, the mass is, sorry, the other way around. Okay, the other way around, times 6. Okay, 40 times 6, around times 6, you get 241. So that means the deflection angle, okay, this is 2, right? Okay, this one, okay, should be 6 times, okay, more deflected because this is lighter, this one heavier. Okay, heavier by how many times? 6 times. Lighter by how many times? 6 times also. So this one, the bond angle should, sorry, not bond angle, the angle of deflection should also times 6 for calcium. So become 12. So which is the closest answer to 12? Okay, the answer is D. Okay, so next time if they give you something like this again, you need to compare how many times there is their mass ratio. Okay, question 3 is about cracking of a hydrocarbon C17H36. Now for hydrocarbon, any hydrocarbon, okay, if undergo cracking, Because of the limited number of hydrogen, it will form, if two products are formed, it will form one alkane and one alkene. Cannot have two alkanes because not enough hydrogen. Okay, so always one alkane, one alkene. So if this is the hydrocarbon C17H36, okay, also the same thing, you will get one alkane and then another one will be alkene. So how do we check whether, okay, all these products, okay, are likely to be produced or not in the reaction? What the method that I use is, okay, I look at this product in A, C3H8. Then C17 minus C3 is C, okay, 14. H36 minus 8 will be, hold on, very bad at calculation, 28. So this is an alkane, and then this one alkene. So is it possible to have this alkene? Yes, the answer is yes. So this one is also likely to form. Now let's look at the second one. Second one is actually an alkene. Okay, so another product will be alkane. The alkane will be C13H28 again. Okay, so this one again is possible to form, so this is also possible. Next one, this is alkene again. So another alkene will form. 17 minus 8 will be 9. 36, so this 20. Okay, this is alkane. Okay, likely to form. And the last one, C16H34, this will be an alkane. So the other product must be an alkene. So let's look at what is left from this C617. After crack to C16, it will be C1, H2. Right, is it possible to have an alkene with the formula C1H2? Okay, not possible. Okay, this, okay, not possible to be an alkene. Why? Because alkene minimum, we must have 2 carbon, because we need double bond between 2 carbons, right? That's a functional group. So you cannot have 1 carbon alkene. That is why if this is not likely to form, okay, this is not likely to form also from the cracking of C17H36 hydrocarbon. That is why, okay, the answer is D, the least likely to be produced one. Now, question 4 is asking you about what's the proton number of an element that has 4 unpaired electrons in its ground state. Okay, by looking at this number, you don't have to check the periodic table. You only need to write, okay, the electronic configuration. So 14, okay, proton number is 14. So remember the way I write electronic configuration are the faster one. So 14, that means 10 plus 4. So that means shell number 1, number 2 must be there because 10 electrons. Okay, 4 more will be 3s2, 3p2. Now for unpaired electrons, okay, for these valence electrons, we need to actually draw the electrons in box diagram. Okay, I'll draw for 3p, 2 electrons. Okay, 3s is full. Now when a subshell is full, it won't have unpaired electrons. So for 14, proton number 14 element, okay, it has 2 unpaired electrons. Okay, what does it mean by pair and unpaired? This one is paired. Okay, unpaired. That means in the box you only have 1. Okay, no pairing. There's no another one to pair with. So 2 unpaired electrons. Now let's look at 16. 10 plus 6. Okay, 1s2, 2s2, 2p6 again. Okay, 3s2, 3p4. Right, here 10. So 6 more here. Again, in 3s orbital, okay, paired electrons. 3p orbitals. I need to put 4, right? 1, 2, 3, 4. So again, only 2 unpaired electrons. Now 22, okay, see here. 22 will be 10 plus 10 plus 2. So 1s2, 2s2, 2p6, 10 electrons. 3s2, 3p6, 4s2, another 10 electrons. Okay, 2 more in 3D orbitals. Here now tricky. 3s subshell full, so all paired electrons. 3p6 all paired electrons full already. 4s2 again paired electrons. So now unpaired electrons in 3D orbitals. So draw the 3D orbitals in box. 5 boxes for d orbitals. 1, 2. Again, only 2 unpaired electrons. So our answer very likely is D. Let's check. So 26, 10 plus 10 plus 6. So 1s2, 2s2, 2p6, 10 electrons done. 3s2, 3p6, 4s2, another 10 done. 6 more, 3d6. So draw 5 boxes for 3D subshell. Put in the 6 electrons. 1, 2, 3, 4, 5, and 6. Okay, this box, 2 electrons, paired electrons. So 1, 2, 3, 4. 4 unpaired electrons. Okay, that is why they say 4, right? The answer is D. Sodium azide NaN3 is an explosive used to inflate airbags in cars when they crash. It consists of positive sodium ions and negative azide ions. What are the numbers of electrons in the sodium ion and also the azide ion? Okay, now here NaN3 you have cation, anion. Okay, this will be cation, and ions will be N3 negative. See, Na is always positive, you know, it's group 1 element. Okay, it forms +1 cation. So to neutralize this, to balance the charge of positive one from sodium, you need the anion to be -1 charge. So the N3 has a -1 charge. Okay, sodium ion, if you look at the periodic table, okay, sodium 11, proton number is 11. Okay, azide is nitrogen actually. Okay, so look at nitrogen 7. Okay, proton number is 7. So number of protons and neutrons will protons and electrons, sorry, protons and electrons will be the same for a neutral atom. Okay, so when we have cation, that means this atom loses electrons. Loses how many electrons? Loses 1 electron here for sodium. So electrons, the number of electrons will be 11 minus 1, 10. Okay, this is proton number. Yeah. Now for nitrogen, you have 3 nitrogen here. That means, okay, 3n, you need to multiply the number of electrons by 3. So total 21 electrons. But, okay, it has a negative charge. Negative charge means gain electrons. Gain how many electrons? Here for -1, so gain 1 more electron. So total 22 electrons. So what is the answer? 10 and also 22. 10, 20, 10, 22. So the answer to this question is B. Okay. Question 6, you are given the structure of an alcohol. Okay, not a very easy question because it involves a cyclic structure in the middle. Okay, this alcohol is called menthol. So this menthol, when it's heated with concentrated sulfuric acid, okay, it forms a few products, and then the products formed include, okay, compound T. That means compound T is just one of the products, yeah. So before you can find compound T, you need to look at the reagent, okay, and try to recall what reaction is this. So you have alcohol. Remember the memory palace thing, yeah? So alcohol on the field, okay, playing the football thing, right? Then this alcohol find it very wet, okay, to play in the acid rain. Therefore, go back to the alkene. Go back to the shaded pathway to the college one. So it got dehydrated. Okay, and it got dehydrated because it was acid rain just now, right? So dry off, become concentrated sulfuric acid. So what happened is it got dehydrated, and when it is dehydrated, you have to remove the OH. Dehydrated means you remove water, right? So remove this OH and then remove one H from the neighbor. Yes, two neighbors. Okay. Right hand side, I focus on this neighbor on top. Okay, so I remove H and OH. So the alkene that I get will look like this. Okay, plus H2O. So let's check whether A, B, C, D, any of them is actually giving you the structure of this first product that I actually draw. Okay, sorry, one product one. Okay, no, okay, didn't give you anything that has double bond here or here. Okay, so that means we cannot sorry, compound T is not a product by removing a H from this carbon on top. There's another neighbor. Okay, that neighbor, okay, use another color. Maybe I just blue, make it blue. Okay, this blue neighbor has another hydrogen also. You see, this is a carbon. It has 1, 2, 3 to an alkyl group. That means there's a fourth bond to a hydrogen. So now product on the left, I want to remove the OH. It got dehydrated, right? Okay. And this H here. So I will get an alkene that will look like this. Yeah, remove OH, remove H. So double bond here. This part became unsaturated. So this is another product. Let's call it product number 2 first. Let's check A, B, C, and D. Any of them actually looks like my product number 2. A, no. B, no. Okay, C is here. The double bond, no. D, okay, the double bond is here. But my one's on the right-hand side. Okay, imagine that. Okay, the same compound, product number 2, this molecule, I've just flipped it. Okay, 90 degrees clockwise. Okay, then it will become compound D. Okay, as long as you rotate, okay, to a certain angle and they become identical, okay, they are actually the same molecule. So this question number 6, the answer is D. Now, I have a sample of hydrated sodium carbonate. Hydrated sodium carbonate formula is Na2CO3. Then inside this sodium carbonate hydrated, right, it has water. But how many water this question doesn't tell us. So I put XH2O. Now you always see this in paper 3 also, right? They want you to find X, so they want you to find the number of water molecule in the hydrated solid. They will give you as X, then at the end you have to find X. So we write the same thing, yeah? XH2O. So this sample contains 25.84% of sodium ion by mass. Okay, what does it mean by percentage? Okay, by mass means, okay, the mass of that element, okay, divided by the total mass times 100. Now, in this case, you see, we don't know what's the mass of everything, right? So what can we do is we can only use their molar mass, okay, or atomic mass to find this percentage by mass. So, percentage by mass of sodium, okay, in the compound is 25.84. Okay, so that means sodium, period table, sodium 23, 23 times 2, because I have 2 sodium here, divided by total of this. So 23 times 2, carbon is 12, oxygen is 16, 16 times 3, okay, plus water is 2 plus 16, so 18x times 100%, I get 25.84. So from here, I'll be able to find x. Let us just quickly calculate. This plus this, I remember from paper 3 is 106, okay? 106 plus 18x times 100 is 25.84. So x is found by 0.2584. 46 divided by this minus 106. I'm just rearranging, yeah. If you cannot understand this one for now, later you have to write down. Okay, step by step, then only you'll be able to figure out this whole thing. But it's just a rearrangement of everything to find x now. So 46 divided by 0.2584, okay, is 178 minus 106 will be 72. 18x is 72. So x is 72 divided by 18 should be 4. Just confirm, yeah, 4. Okay, so now I know that this x is 4. This formula is actually Na2CO3, okay, 4 water in the solid. Now, this one is useful. Okay, 35.6 gram of hydrated sodium carbonate. I can find number of mole because now I know the full formula. Okay, if I know the full formula, I can find the MR. Okay, 106, okay, plus 18 times 4. How do I get 106? Because I've calculated from here just now, right? Okay, so it would be 106 plus 72. 178. Oh, okay. Oh, sorry. I found the total here already just now. Okay, it's okay. So 178 will be the molecular weight. And then now I can find the number of mole of the hydrated solid. 35.6 divided by 178. That would be 0.2 mole. Okay. Now, if I have 4 water in the solid and I heat this solid, okay, I will get anhydrous solid, anhydrous compound. Okay, water will be removed. So 4 water molecules will be removed. So 1 mole of hydrated sodium carbonate, okay, will give off 4 moles of water. Yeah, so number more of water that will be given off, okay, by this 0.2 moles of hydrated sodium carbonate will be 0.2 times 4. Why? Because 1 mole, okay, will give 4 moles of water. So 0.2 moles will give 0.2 times 4 moles of water. So the answer is 0.8 mole. But of course, haven't done yet because they want the mass of water. So this number of mole of water will be 0.8, okay, times the molar mass of water 18. Okay, why 18? 2 plus 16. 2 hydrogen, so 1 times 2, then water is 16. So 0.8 times 18, 14.4 gram. Therefore, the answer to this question will be C. So how do we find hybridization? You know, they only want carbon atoms. Okay, only carbon. Carbon 1, 2, 3. So label already. 1 here, 2 here, and 3. Okay. Now, hold on. They say carbon, okay. Oh, sorry. Carbon atoms 1, 2, oxygen 3. Okay, I thought all carbon atoms. Okay. Now let me give you a rule to make this faster, yeah. For carbon, nitrogen, oxygen. Now your syllabus will only talk about hybridization of these three elements: carbon, nitrogen, oxygen. They are all the same. Okay, whenever you see carbon surrounded by all single bond. Okay, no double bond. Okay, all single bond, yeah, must be sp3 hybridization. Now, when you see double bond, one double bond, okay, it will be sp2 hybridization. For carbon, all single bond, like this carbon here, all single bond, right? 1, 2, 3, 4. Maximum 4 only. If 4 also single bond, this carbon is sp3 hybridization. Okay, how to know 4 then sp3? Okay, this 1s plus 3p. Total is 4, right? So 4, 4, sp3. Now, if there's one double bond, like this carbon here, there's one double bond. Okay, sp2 hybridization. Bonded to 3 groups only. That's why you need 3 orbitals. Okay, and what else? Okay, if you see a triple bond, there will be sp hybridization. Now, I haven't touched 2 double bonds. If 2 double bonds, then also sp. Okay, or 2 double bond. Okay, sp hybridization. Let's look at, we always see carbon. Okay, let's just look at maybe nitrogen. Okay, now nitrogen, this nitrogen, all single bond. Okay, all single bond. That is why, okay, also sp3. Yeah, but nitrogen is unlike carbon. It doesn't form four single bonds. I look at these 3 single bond. How do I know it's sp3? Because this nitrogen has a lone pair. Okay, that lone pair is actually counted in also. But I don't want to make your life so difficult. Okay, as long as you see everything single bond. Okay, single bond, okay, including this O also all single bond, right? So sp3 hybridization. Yeah. So this is, I think, it's a faster way to solve this question. Okay, so now let's try out all these. Yeah, I have carbon number 1. I have a double bond. See, if one double bond, what's the hybridization? sp2. Now, carbon, there's label number 2, all single bonds. So this is sp3, all single bond. Okay, sp3. Now, oxygen, okay, number 3, again, all single bond. You don't see any double bond, right? All single bond, another sp3. So sp2, sp3, sp3. Let's look at the answer. sp2 correct. Okay, this or this. Number 2, sp3 still correct. This or this. Number 3 should be sp3. So the answer to this question is B. Okay, so just remember this one, then you'll be able to solve the questions like this one. Ask you to determine the hybridization of which atom inside a very big molecule. Okay, all single bond sp3, one double bond sp2, a triple bond or 2 double bond sp. Yeah. Now I want to also, because we have seen this question now already, I want to also tell you, if you see oxygen in oxygen gas O2, it's double bond. So you see one double bond. So this oxygen is sp2. Now there's another thing called carbon monoxide gas, right? C triple bond O. So this O now has a triple bond. So sp hybridization. Okay. So nitrogen, in nitrogen gas N2 triple bond, this nitrogen sp hybridization. So just want to give you more examples that you have seen it here now. At least, you know, when you see them in the exam, if you can remember, okay, you're lucky enough to remember all this, then you'll be able to solve the question faster. Yeah, but I'm actually still following this faster rule that I told you. Yeah. Question 9 about aluminium chloride. Aluminium chloride has which one is correct? Which one is correct? Aluminium chloride has a much higher melting point than magnesium chloride due to the small size of aluminium ion. Okay, right. Aluminium chloride is actually covalent. Okay. Magnesium chloride is ionic. So a covalent compound will not have higher melting point than ionic compound. So this part is not correct. So A is incorrect. Now B, anhydrous aluminium chloride reacts vigorously with water to form a solution with pH greater than 7. Remember in paper 2, we talk about aluminium chloride also. Okay, aluminium chloride, because it's covalent, it can be hydrolyzed and form acidic solution. Yes, it reacts with water, but form acidic solution. If solution is acidic, the pH should be lower than 7. So this word greater is not correct. B is not correct. C, each aluminium Al2Cl6 molecule found in aluminium chloride vapor contains 2 coordinate bonds. Okay, this whole statement is correct. It has 2 coordinate bonds, correct. Al2Cl6 in vapor, also correct. So C is correct. Now, if you cannot remember, okay, AlCl3, okay, like this, and then you have another AlCl3. Sorry, Al. So because this Cl has lone pair electrons, okay, all of them actually has 3 lone pairs electrons, yeah, but I thought want to just skip and don't draw everything, but it's okay. Might as well just put the dots in. Okay. So Cl, okay, can donate one of its lone pair electrons to aluminium because aluminium has only 6 electrons around it. It is electron deficient. Okay. So same goes to this aluminium with this chloride. So between Al2Cl6, the two AlCl3 molecules, there are 2 coordinate bonds. So C is correct. Now let's check why D is incorrect. The bonding between aluminium chloride is strongly ionic due to the large difference in electronegativity. Okay, this part is not correct. Okay, we already know that it is covalent. Okay, so not ionic. That is why the answer is C. Okay, now question 10. 4 compounds here are shown. And how many of these compounds have an odd number of sigma bond? Let's draw the structure of every compound. Now, C2H4 is an alkene. Okay, C2H4 is an alkene, so the structure looks like this. C2H5OH is alcohol. Okay, saturated alcohol, so there's no double bond. Draw the structure. It will look like this: CH3, CH2OH. CH3, CHO, if you see CHO at the end, it is an aldehyde. Okay, so the structure is CH3, CHO. C double bond O, carbonyl compound, yeah? CH3COOH, okay, we are very familiar with this one. It's carboxylic acid. Now, let us just draw the structure of this CH3. COOH. Sorry, forgot the OH bond. So we are supposed to look at the number of sigma bond. So all single bond, okay, are sigma bond. Okay, double bond is 1 sigma bond plus 1 pi bond. Triple bond is 1 sigma bond and 2 pi bonds. Okay, yeah? So knowing these three concepts, you'll be able to find the number of sigma bonds in all these compounds. All single bonds are sigma bonds. if you see double bond, that means there's 1 sigma and 1 pi. Triple bond will be 1 sigma bond and 2 pi bonds. So let's look at C2H4 alkene. Single bond, sigma. Single bond here, sigma. A double bond here, there's a sigma, there's a pi bond. Sigma bond here again, sigma bond here again, because single bond. So total 1, 2, 3, 4, 5. Okay, odd number of sigma bond. This one is, let's put a tick. Later we count the tick because they ask how many compounds have odd number of sigma bond, right? Okay, now let's look at the alcohol. Single bond, sigma. Single bond, sigma, single bond, sigma, single bond, sigma, sigma again, sigma again, sigma again, sigma again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, even number, not odd number. Cross. Okay, aldehyde, sigma, 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 sigma. Double bond, 1 sigma, 1 pi. Single bond again, sigma. 1, 2, 3, 4, 5, and 6. Oh, again, even number of sigma bond. So cross this again. The last one, sigma, single bond, sigma, single bond, sigma, single bond, sigma, single bond, sigma, double bond, 1 sigma, 1 pi bond, single bond again, sigma bond, single bond again, sigma bond. 1, 2, 3, 4, 5, 6, and 7. Okay, so that would be odd number. So another tick. 2 compounds, okay, 2 compounds with odd number of sigma bonds. So the answer is B. So yeah, this question you have to draw all the structure of compounds because you need to know where are the sigma single bond and double bonds. Okay, some of them might contain triple bond. Yeah, be careful because nitrile is also one of the functional groups in AS Libus. So nitrile, C triple bond N, right? So the triple bond, there's a sigma bond and 2 pi bonds. They can change this question anytime to how many have odd number of pi bond, right? Okay. Question 11. A flask Q contains 5 liter of helium at 12 kilopascal pressure. Flask R contains 10 liter of neon at 6. Now they want to connect these two flasks. Okay. First, I have one flask. Okay, let's say they are not connected at the beginning. Here I have, okay, this Q is R. 5 liter, 12 kilopascal. I should have drawn it bigger, 10 liter, 6 kilopascal. Now at the end, we connect them. Okay, I remove this partition. Okay, remove this. Now they're connected. So what will be the final pressure? Now, usually I solve this very fast by using P1V1 plus P2V2 equals to P3V3. Now, this 3 will be the final one. Maybe I change it to P final, V final. Okay. This is actually following the ideal gas equation. It should be PV over nRT. Okay, 1, 1, 1, okay, plus P2V2 over nRT2 equals to P3V3 over nRT3 of final, yeah? It should be like this, but I actually removed the temperature because you see, they didn't talk about the, they say the temperature is constant, right? So I removed the temperature. Okay, they're all the same. Then N and R, the number of moles are also the same, right? So I remove. That's why at the end I simplify to this. I realize that people will always ask this sort of question. Okay, that is why this formula, this simplified formula, can also always be used for this sort of question. Yeah, this sort of question came out many times already. So after you solve this one, okay, you go and find another similar one and then solve again. You don't need to find many variants. I believe that, okay, every year will at least have one variant, okay, with this sort of question. So go and find those questions and practice a few more times. Then you'll be fine with remembering this formula. Okay, now let's see how to use this formula. P1, so everything in Q, okay, I use 1. So P1, the pressure one will be 12 kPa. Okay, let's just don't write the unit anymore. Okay, to save time, because it's paper one, right? What do you want to do is always save time. V1, 5, so times 5, plus P2, V2 now in flask R, yeah? P2 is 6. Okay, volume, 10. So what's the PFVF, yeah? After they're connected. Okay, after they're connected, we want to find the final pressure. So of course, we don't know PF. That is our unknown. Now, that means V is known. So what is V? After we connected, right? Total volume. Total volume 5 plus 10. 15. Okay, so rearrange the formula. Okay, this equation. You'll be able to find that 12 times 5, 60 plus 60 divided by 15. 120 divided by 15. The answer is 8. So if unit is kilopascal, that is why 11, the answer is A. Now this SiO2, the name, including the oxidation number of silicon, is actually called silicon 4 oxide. A4, A6. Rana, erase. Okay, silicon 4 oxide. Okay, it's the systematic name of this SiO2. Now, this SiO2 actually has a giant covalent structure. Yeah, I show you the next slide, which is actually my slide in chapter 5. So this silicon 4 oxide has a giant molecular structure, or we call it giant covalent structure, that looks like this. Look at the diagram, it's easier to see the diagram. Now, in this diagram, I have atoms with 2 different colors, the blue one and the brown one. Now, the blue one is silicon. The brown one is oxygen. SiO2, right? You have 2 types of elements, silicon or oxygen. So this diagram is that giant molecular structure. So can you see that in this structure, every silicon, okay, every silicon here, okay, I use this in the middle, yeah, is bonded to 4 oxygen. The blue one is bonded to 4 brown ones. So each silicon is bonded to 4 oxygen, but every oxygen, the brown one here, is only bonded to 2 silicon. Yeah, again, find another one. Okay, here is brown one, bonded to 2 silicon. Okay, there is no way to explain this one within your syllabus. This is actually beyond your syllabus, why it is arranged like this. Now, every time something is bonded in a giant lattice, okay, the way they are bonded to each other is actually to maximize, okay, to always maximize the strength of the bonds, and at the same time to minimize the repulsion. So all oxygen here will actually have lone pair electrons, okay, because they are only bonded to 2 silicon, right, covalently. So yes, 2 lone pair. So they have to arrange in a way that oxygen, the lone pair and lone pair, can be further from each other as possible. At the same time, not so much repulsion between the lone pair and the electrons from silicon. So at the end, they arrange in a pattern like this. So yes, okay, so my what I'm trying to tell you is for this case, you have no choice but to remember the structure like this, the diagram, and also how they are bonded to each other. Silicon for oxygen, okay, oxygen to silicon. You, unfortunately for this question, okay, unfortunately for this question, you cannot look at the formula and say, oh, every silicon is bonded to two oxygen, okay, and every oxygen is bonded to only one silicon. No, okay, it is every silicon for oxygen, every oxygen two silicon atoms. Okay, and the bond is covalent. That is why for this question 12, X is 4, Y is 2, okay, Z is covalent. So 4, 2, covalent. The answer is C. Question 13 is not a very difficult question. The difficulty is only about choosing which reaction for you to refer to. Okay, which reaction for you to refer to in order to get an enthalpy change for the following reaction, this reaction. Let's look at the reaction first, because we want to find delta H for this reaction, right? So this reaction is our main focus. Now, in this reaction, I have gaseous carbon atom, gaseous hydrogen atoms. Now, if they give you everything in gas, it's a good news because gaseous atoms means they don't have bonding between each other. They are far apart from each other. So you don't have to consider how do I break them so that they can become gas. Okay, no, they are already in uh, gaseous form. So this C2H6 ethane has one CC bond and 6 CH bonds. Yeah, if you draw the structure, one CC bond, okay, 6 CH bonds. And you see here, all also gases, okay, gaseous atoms. So now let's look at the 4 other reactions that are given to us with their enthalpy change. Which one are the closest to the reaction you want to focus on? Yeah. Look at the first one, carbon on the left, but this is a solid. So if it is solid, I have to think about how to vaporize this carbon solid to gaseous carbon atoms, right? So if can, I don't consider this first. Let me cross out everything that has a solid carbon. Okay, because I want to find the closest one. I want to see gaseous carbon atoms in the equation. So here I found this. Okay, let me put a tick here. I want this because it has gaseous carbon atoms. Now next, I hope to see gaseous hydrogen atoms, not H2. I want only H. Yes. So here I have H2. That means I need to consider about breaking the H2, right? H and H single bond. So hopefully don't have to look at this one. The one this also. Another tick here. So very highly likely I'm going to use equation number 3 here. Because it's gaseous carbon, gaseous hydrogen. I know a different side, but it's okay. Okay, we know we can change the sign of the delta H by changing their side, yeah. And then here, since I don't want this already, so I don't want equation 1, I don't want equation 4. Let's look at what is equation 2. Equation 2 is irrelevant at all because I don't want CO2, I don't want water, I don't have O2, okay. CH4, yes, but since 3 species I already cannot use the information, so let's not use equation 2 also. So that means, okay, we will choose equation number 3 to refer to for our delta H. Now, equation number 3, CH4, okay, CH4, methane has 4 CH bonds. 4 CH bond, no CC bond, it's okay. 4 CH bonds, and breaking the 4 CH bonds, it needs this much of energy, 1648. Breaking of bonds, okay, breaking bonds is endothermic, okay, or positive delta H. But here in our reaction, we want to form 6 CH bond. Formation of bond, okay, is exothermic. So, which is fine. Okay, I find the bond energy of CH bonds, then I change the sign, it becomes exothermic. So from equation 3, I'll be able to find how much energy is needed to break one CH bond, which is 1648 divided by 4. Okay, to break one CH bond, I need 1648 divided by 4, which is 412 kilojoule per mole. Yeah. So using it here means formation of one CH bond. Okay, formation of one CH bond is negative 412. I reverse the reaction, so I change the sign from positive to negative also. Right? Here is breaking CH4. Here formation of C2H6. So we reverse, okay, the reaction. We change the sign from positive to negative. Here positive, right? So here will be negative. Now 6 times 1 CH bond, negative 412. So 6 CH bond will be negative 412 times 6. Calculator, times 6. Negative 2472. Sorry, my writing's bad. 2472. Okay, now negative 2472 is only for CH bond. Do you remember that we still have one CC bond? Right, since these few equations are not able to provide us with that, we look at the bond energy. Don't forget we have another table. Here we have the CC bond. Formation of bond always exothermic. This one given to us is bond energy, okay, which means breaking of the bond. So again, we change the sign to negative. Okay, formation of one CC bond, exothermic again. So we change this to negative 350. So the total enthalpy change for this reaction will be negative 350, okay, plus negative 2472. Sorry, I have very bad writing. I rewrite here again, negative 2472. Our answer is negative 2822. So the answer is A. Now, question 14. Question 14 is again enthalpy change question. This is standard enthalpy change of neutralization. How do I know? Because I have sodium hydroxide and hydrochloric acid, aqueous solutions of these two, acid and base. So this is a neutralization reaction. So that means we are calculating the enthalpy change of neutralization. Now, these are question, I know they haven't asked anything yet, but the first thing I always do is I write down the equation so that I know the mole ratio. Of course, in this case, they give me sodium hydroxide and HCl, okay, which is 1:1 mole ratio. This is very straightforward, but they could give you other acid, okay? So always write the equation so that you know how many moles of water is formed from the neutralization. Why do I find the number of moles of water? Because the definition for enthalpy change of neutralization is enthalpy change when 1 mole of water is formed from the reaction between acid and alkali. Okay, so it's about the number of moles of water that is formed from the neutralization. Now I'm given the concentration and volume of base, volume and concentration of acid. Why they gave us this? Because we can find the number of mole, then we can find the number of mole water that is formed. Okay, so this number of mole of NaOH will be mu over 1000, 0.350 times 25 divided by 1000. That would be 0.35 times 25. 8.75 times 10 to the power of negative 3. Can you see the acid also same concentration, same volume? So number of mole acid is also the same. 8.75 times 10 to the power of negative 3, because I'm going to use the same formula to find them anyway, right? So 8.7, okay, according to this equation, one mole of sodium hydroxide reacts with 1 mole of HCl to give you 1 mole of water. 111. So 8.75 times 10 to the power of negative 3 moles of sodium hydroxide reacts with 8.75 times 10 to the power of negative 3 HCl. We get the number of mole of water to be the same. Yeah, right here. So the number of mole of water from this reaction will be 8.75 times 10 to the power of negative 3 mole. Yeah. And now we need to find the heat, the amount of heat that is being produced by this neutralization. Use this formula Q equals to mc delta T. When you are mixing two solutions together, the total volume will be the M that we're going to use. I know M means the mass, but we always assume that 1 centimeter cube of the solution has 1 gram. Okay, 25 here plus 25, total volume is 50. C is given. If it's not given, you find from the table in the question paper at the end, right? The table of important values. But here you are given, so 4.2. Delta T is given to us, temperature increases by 2.5 degrees Celsius. Now, of course, we have to actually use Kelvin, but when it comes to temperature change, okay, the temperature change in degrees Celsius and temperature change in Kelvin will be the same because you're deducting from two values, right? So they will be the same. So 2.5. Okay, now 50 times 4.2 times 2.5, 525. Okay, joule. In this case, it's still in joule, yeah? Okay, because all the units, see, J here, no more other unit for energy. So this is the unit for Q for now. And then, okay, we cannot stop here because we want to find the molar enthalpy change. That means must be per mole of water. So delta H will be Q divided by N. The N here depends on which standard enthalpy changes that you're talking about. In this case, standard enthalpy change of neutralization. So the number of mole is the number of mole of water. Okay, if you go back and look at all the definitions for the enthalpy changes again, in the definition, you always mention 1 mole of something, 1 mole of something, right? So per mole, the mole is always based on the number of mole of that particular substance in the definition, right? So in this case, water. Now, enthalpy change of neutralization is always exothermic. And always exothermic, always release heat, yeah, neutralization. So we need to include a negative sign here to represent exothermic reaction. So negative 525. Don't forget to divide by 1000 because delta H, the unit is always kilojoule. Okay, here we always stop at joule. You can, of course, continue to convert it first, okay, or you can convert in this formula, right? And then divide by the number of mole of water. We found them already just now. We found the number of mole of water here. Now let's find the answer. Divide by 8.75 times 10 to the power of negative 3. So I got 60 as the answer. 60, negative 60 kilojoule per mole. So the answer is B. Okay, negative 60. Which compound has an MR molecular weight of 84 and will react with HBr? Give a product or with an MR of 164.9. Now, before we start, okay, there's a lot of methods. There are many ways to actually rule out the answers before you start. They give molar weight, okay, molecular weight 84. So A is a cyclic compound C6H12. Count the number of carbon 1, 2, 3, 4, 5, 6. Okay, every carbon bonded to 2 hydrogen. So C6H12. But A is an alkane, yeah. Alkane will not react with HBr. Okay, will not react with HBr. Let's just rule out A. Is there any other alkane? No more alkane. Then B is an alkene. Alkene will react with HBr. Okay. D is also an alkene, will also react with HBr. C, can you see the C double bond? O, it is a carbonyl compound. In this case, it is a ketone, not aldehyde, because the CO is in the middle of the molecule. It will not react with HBr. No. Okay, so again, rule out C. Now only look at B and D. And then we see which one has a molecular weight of 84, yeah? B, 1, 2, 3, 4, 5, 6, 7 carbon, hydrogen, this is alkene, right? So CnH2n. So it will be C7H14, D, 1, 2, 3, 4, 5, 6 carbon, alkene, CnH2n general formula. So H will be 12 here. So which one has a molecular weight of 84? 12 times 7 already 84, right? Plus 14. Oh, this is definitely more than 84. B is not the answer. Let's look at D. C times 6. 12 times 6, 72 plus 12, 84. 84 and will react with HBr. I don't even have to check the product whether it's 164.9 or not. I know the answer is D. So if there's a way for you to reach the answer before you have to write everything down, okay, we try to avoid all those, okay, because in paper one, what's our main goal? Our main goal is always to save time, right? Of course, now you know this discussion, right? So let's just try C6H12 plus HBr, alkene with HBr addition, electrophilic addition. So at the end, you get C6H13Br. So here we already found is 84 plus HBr. H is 1. Br is Br 17. Okay, 79.9. Let's see. 84 plus 80.9. 164.9. So we confirm our answer. Now you already confirm your answer once you finish everything and then you want to check, double confirm your answer. Then you do this. If not, we already knew the answer is D before we reach 164.9. Okay, when it comes to this sort of question, you only need to balance the number of moles of the reactants where their oxidation state change in the reaction. Yeah. Here it says that 2 moles of VO2 positive reacts with 1 mole of zinc. That means my equation, I have to write 2 VO2 positive, okay, with 1 mole of zinc. Now this part is balanced for you already. Okay, what are the products? Zinc ion, zinc 2 plus, and Y plus Y. Now can you see that on the left hand side, I have this vanadium ion, okay, ions with vanadium, yeah, 2 of them. Here there's Y, I know, but if you look at all the answers, Y contains only 1 vanadium. Here I have 2, right? So that means 2y will be produced. They didn't balance this for you. Okay, I deduce this from the answer. Okay, y contains only 1 vanadium, but I use 2 from beginning. So that means 2y will be produced. Yeah, so understand this part first, like why did I write like this? I'll continue. And I'll give it a bit of time to process. Let me drink water. Losing my voice. Okay. Right. Now I'm going to continue now. I'm going to find the oxidation states of vanadium and zinc on both sides. Why? Because question tells me that only zinc and vanadium change oxidation state. You see, in the presence of acid, so acid is involved, but acid, the H plus oxidation number didn't change from beginning until the end, so I ignore. I don't write them in the equation. So paper 1 question for this type of redox reaction is like this. Whatever elements, species that oxidation numbers don't change, okay, we ignore. Yeah, we only wrote this. Now, zinc here element, oxidation number 0. Okay, oxidized to zinc 2 plus. So oxidation number changed from 0 to +2. It is an oxidation. Okay, oxidation, because oxidation number increases. Okay, now increase by how much? +2. Yeah. Then vanadium here, I will find oxidation number. This one is slightly more working because I need to use X. X unknown, yeah. +2 times -2 from oxygen. Oxygen always form oxide, right? It always accept 2 electrons. Okay, overall charge is +1. I can find the X. Okay, X is +1. Here is -4, right? Move over to the other side, +4. So X here is +5. Yeah, this part okay, yeah? So this vanadium here has an oxidation number of +5. Then it becomes Y. Y is a species that I don't know. Okay, but it is okay. Why? I know the change in oxidation number of zinc is +2, increased by 2. Increased by 2 means zinc is actually donating 2 electrons. It loses 2 electrons to form a +2 cation. That 2 electrons will be accepted by 2 VO2 positive ion. Yeah, and form Y. Yeah, this one loses 2 electrons. The 2 electrons are accepted by these 2 cation. Yeah, 2 VO2 positive accepts 2 electrons. So 1 VO2 positive accepts 1 electrons. Okay, here the overall change is +2. This one reduction, overall change must be -2. +2 -2. Yeah, so that means each of these one will be -1, the change. So +5 times 2, okay, -2 will become a +4 times 2. Again, I know it sounds very confusing again. So zinc loses 2 electrons. That's why the change is increased by 2, the oxidation number. These 2 electrons, where did they go? Okay, they are accepted by the 2 cations. two cations accepts 2 electrons. That means each cation accepts 1 electrons. The oxidation number of vanadium in one cation is +5. Okay, each of them accepts 1 electrons, right? So +5, add 1 electron, that means -1 will become +4. Why did I put the 2 in front? Because there's 2 cations here. So 2 cations, each of them accept 1 electrons. So overall is -2. So became new, okay, new ions. And then the new ions, each of them will have a vanadium with a +4 oxidation state. Yeah. So now I know why it must be a vanadium ion, okay, with the oxidation number of vanadium being +4. So I look at these 4 answers, A, B, C, D. I find which vanadium has an oxidation number of +4. So our goal is find which one has +4 oxidation number. Let's look at A. AVO3 negative. Okay, X plus 3 times -2 equals to -1. So what is X? X is -1. Here will be -6. So here +6 +5. Is it +4? No. Okay, A is not the answer. Now B, VO positive. Okay, X plus -2. Oxygen is always -2, right? It's oxide ion. The +1 or charge. X is +1 +2 equals to +3. Is it +4? Again, no. Okay, C, VO 2 positive. Okay, X plus -2 equals to +2, the overall charge. X is +2 +2, +4. Is it +4? Yes, the answer is C. Let's check if D, okay, is also the answer or not the answer. VO2, 2 positive. X plus 2 times -2 equals to overall charge +2. X is +2 +4, which is +6. Is it +4? No. So confirm that the answer to this question is C. Yeah. So now we have finished discussing this question. Now we look back at this equation again. Okay, can you see that I actually don't include other reactants and other products? Okay, I only focus on those that their oxidation states they changed in the reaction. So paper 1, again, when you have to write equation, balance equation, or find the other species, okay, you have to do like this. You only need to find what's the change of oxidation number in oxidation. Okay, should increase, yeah? Increase by how much in total? Decrease by how much in total? Then divide by the number of the moles. Okay, to find what's the change in only one. Okay, in only one molecule or in only one ion or one species. Then you'll be able to find the answer. Now, this question is actually taken from past year, but it is modified. Okay, in past year paper, the question doesn't have this oxidation number given. So the setter actually modified the question and added this oxidation number, okay, into the name of the ion. Now, nitrate ions. Nitrate ions, when you see ATE, okay, meaning this nitrogen, the element is being paired, okay, with oxygen. Can be any number of oxygen, can be NO2, can be NO5, NO3, right? You know, nitrate, there's nitrate and nitrate ions, right? So O can be any number, but as long as that element is paired with oxygen, okay, to form an N-ion, the name of the N-ion will end with ATE. Now, the one in bracket is the oxidation number of the element that is paired with the oxygen. So this 3 is actually the oxidation number of the nitrogen in these nitrate 3 ions is +3 because of here. Okay. They say that ammonium ion is being converted, right, to these nitrate 3 ions. So what is the change in the oxidation number? Since this is already given to us +3, what do? Is we find the oxidation of nitrogen in the ammonium ions. Hydrogen is always +1 because it has only 1 electron and it loses the electrons very easily to other atoms. Okay, so always +1. So this is X unknown, right? X plus 4 times ammonium, 4 times +1. Overcharge is +1. So what's X? X is +1 minus 4, -3. So here, -3. -3 to +3, what is the change? Okay, the change is +6. That is why the answer B. Now, if this 3 in Roman number is not given to you, they only say nitrate ions. Yeah. If there is no number given to you in the, okay, no Roman number given to you in bracket, they only say nitrate ions, we always assume that it is NO3 negative. If NO3 negative, you have to find the oxidation number of nitrogen. Okay, X plus 3 times -2 equals to -1. X equals to -1. Okay, here will be -6, here +6 is +5. So again, ammonium to NO3 negative, here -3, here +5. So what's the change from -3 to +5? Increased by 8. This increased by 6, increased by 8. That is why when you practice with your past year paper, okay, without the Roman number in bracket, okay, you found that the increase is +8. Okay, but when it is given here, okay, then it saves you time on finding the oxidation number. This is +3 here, so the increase is +6. Question 18, hydrogen peroxide decomposes slowly at 20 degrees Celsius to form water and oxygen. Okay, you're given the equation with equilibrium constant Kc. Now, the reaction is faster when a catalyst is present. Which statement is correct? Okay, A, the catalyst alters the Boltzmann distribution so that the reactant molecules have more energy. Catalyst will not change the distribution. Okay, it doesn't affect the distribution. Catalyst is only changing the position of activation energy to the lower one, right, in the Boltzmann distribution. So this catalyst, okay, alters this Boltzmann distribution is not correct, yeah. And it doesn't make the reactant molecules to have more energy. No, reactant molecules won't gain more energy just like that. Okay, they only gain more energy when temperature is increased. So catalyst does not affect the energy of the reactant molecules. B, the catalyst has no effect on the value of Kc. Okay, B is correct. Catalyst will not change the value of Kc. Remember, Kc can only be changed by temperature. Kp also can only be changed by temperature. All equilibrium constant. In AS, you're only learning Kp and Kc. In A2, you have 4 to 5 more equilibrium constant to learn. They are all the same. They can only be changed by the temperature. Okay, so B is the answer. Let's also look at why C and D are not correct. Yeah? C, the catalyst increases the values. Okay, already say has no effect, right? So increasing the value of Kc is not correct. D, the catalyst provides a different reaction mechanism with a higher activation energy. It's lower. Right? If it is higher, then what's the point of using catalyst, right? So we don't use catalyst if it will, okay, it will actually make the activation energy to be higher. Okay, it will always make activation energy to be lower. So this answer is B. Okay, next one is question 19. Okay, question 19 is another more difficult type of equilibrium question because it is actually changing two conditions at the same time, right? One will be increasing the temperature, the other one will be decreasing the pressure. Yeah. So two conditions are changed. Temperature is increased, pressure is decreased. So A, H2, CO2 becoming water and carbon monoxide. Left hand side, 2 moles of gas. Right hand side, also 2 moles of gas. So decreasing the pressure, okay, will not change the equilibrium position, yeah. But okay, delta H is positive, endothermic reaction. So increasing the temperature. Now, whenever we talk about changing the temperature, I would like to look at the delta H. I prefer to look at delta H, and if endothermic, right, I'll add heat on the left hand side as one of the reactants. It is not exactly a reactant, but this reaction needs heat, right? Then only can form product because it will absorb energy. So you see, if I increase the temperature, okay, that means this heat is being increased, right? The reason why I put heat in the equation is so that you now can treat heat as one of the reacting species. Yeah. So if I increase the temperature, see heat is on the left, right? So if this heat, the concentration is increasing temperature is just like increasing the concentration of heat. So left hand side, you have heat, temperature is increased, this concentration increases. So equilibrium position will actually shift to the right hand side. Right hand side, correct. Okay. Moving to the right hand side, and then if we decrease the pressure and then no change to the equilibrium position. Let's look at B. B, left hand side, I have 1 mole of gas. Okay. B, sorry, right hand side, I have 2 moles of gas. So delta H is again endothermic, so I add heat to the left hand side, because endothermic means absorb heat. Okay. Again, if I increase the temperature, okay, equilibrium will shift to the right. How do I write this? Hold on. Increase T. Okay, move to the right. Decrease P. Here also, increase T, move to the right. Decrease P, no change. Okay, now decreasing the pressure, okay, decreasing the pressure will actually makes the equilibrium to shift to the position to favor, okay, to favor the reaction that will produce more moles of gas. So shifting to the right hand side, because right hand side you have more moles of gas. Oh, okay, wait, I should have written this one, yeah, but yeah, it's correct. Okay, right hand side. So both also to the right hand side. Okay, that is why the answer is B. But let's check C and D also. Now C, I have total 3 moles of gas on the left, 2 moles of gas on the right. Okay, and also here delta H is negative. That means this time the reaction is exothermic. I put heat on the right hand side. Heat is one of the products. It releases heat, right? So heat is one of the products. So I put heat on the right hand side. If I increase the temperature, this is increased, right? So equilibrium will shift to the left. Okay. Then now I also decrease the pressure. If I decrease the pressure, okay, equilibrium will favor the direction to produce more moles of gas molecules, which is again to the left. Okay, so both to the left, we want both to the right hand side, right? So C is not correct. Just like A also not correct. I forgot to cross. Last one, D, 2 moles of gas on the left, 2 moles of gas on the right. Okay, reaction is exothermic, so add heat on the right hand side. increase the temperature, equilibrium will shift to the left. Okay, decrease the pressure, equilibrium, no change because both sides you have the same number of gas molecules. So the only answer that will give you both also moving to the right hand side, okay, both equilibrium of position move to the right hand side is B. That is why 19, the answer is B. An acid with 2 hydrogen atoms per molecule will be stronger than an acid with 1 hydrogen atom per molecule. Now, this one is not always correct because how do I say? What if the molecule with 2 hydrogen atoms is a carboxylic acid, COOH. Yeah, COOH. Now, carboxylic acid is an organic acid. It is actually always weaker than inorganic acid. So if I have this and I have HCl, although HCl has only 1 hydrogen atom per molecule, carboxylic acid is carboxylic has 2, but HCl is still a strong acid, and okay, carboxylic acid is still a weak acid, so it won't be stronger than HCl. So this is not always correct. Okay, now B, answer B, a concentrated solution of a strong acid will have a lower pH than a dilute solution of a weak acid. Okay, strong acid doesn't have to be concentrated. Okay, doesn't have to be concentrated. Already most of the time have a lower pH than a dilute solution of weak acid. Okay, now we're talking about a concentrated one. So definitely will have lower pH because the concentration of hydrogen ion will be higher. So definitely lower pH. So B is always correct. Okay, dilute solution of strong acid probably won't have a lower pH than a dilute solution of weak acid. Yeah, not all the time, but concentrated one definitely will have lower pH. Now C, a concentrated solution of strong base will have a lower pH than a dilute solution of weak base. Now concentration of strong base, that means a lot of hydroxide ions. So the pH will be high, not low. Okay, bases will have pH values more than 7, which is high. Okay, acids one, more concentrated, stronger acid will have lower pH, but strong base will have higher pH. So this word is not correct, should be higher. Last one, a strong acid is more dissociated in solution than a strong base. No, both strong acid and strong base, they are fully dissociated in solution. Full, 100%, both also 100%. So we can't say which one is more dissociated. Okay, so the word more is not correct, should be same, okay, dissociate to the same extent. Yeah, both also 100%. So not correct, not correct. So 20, the answer is B.